With section 5.6, we're talking about manipulating logarithmic expressions. And that just means changing them into different forms so that they're easier to deal with. So here's the notes, the two learning targets here. One, you can take a logarithmic expression and you can condense it into a more concise, small expression like that. Or you can take a small one and you can expand it into different ones. So these work both ways. These are three rules, but they work both ways. If you have log base b of x plus log base b of y, what you're doing, remember, every time you take a log, you're finding the exponent. And if we do the exponents and we add the exponents, what we're doing is we're actually multiplying the bases. And that's what the x and the y are in this case. Those are the bases. Those are the things that we're taking the log of. If you subtract exponents, you're dividing. Now, one thing you do need to notice, for every single one of these, the base is the same thing. The log base b of x plus the log base b of y, and the base is b over here as well. The log must match for you to use these rules. And just to give you an idea of how it works, let's look at an example where we actually put some numbers in here. Let's say the log base 2 of 4 plus the log base 2 of 8. So if we do this, we should end up getting, what is the log base 2 of 4? Well, that's 2. 2 to the second power is going to give us 4. What's the answer to the log base 2 of 8? Well, what power do we raise 2? 2 to get 8, that would be 3. So we get 2 plus 3, which is 5. Now, if we didn't do that, if we condensed them first and then evaluated, since we're adding here, we're going to multiply the bases. So what we'd end up with is log base 2 of 4 times 8, which is log base 2 of 32, which the answer is 5. So that's how this thing works. All you're doing is you're finding the powers, adding them together, but in this case we're doing it, let's say we can't actually find the powers by hand or in our head and we don't have calculators handy. We can do this and we can combine them together to find out what we're actually looking for. And the same thing with division, and here is the power. What we're really doing is we're taking this power right here and we're moving it out front. And the reason why this rule works is this. If we have x, well, let's do it this way. If we have 2 squared to the third power, and we have a log base 2. So let's take this out just a little bit. Let's back up just one more step and do 4. So log base 2 of 4 to the third power. Instead of evaluating 4 to the third power, then taking the log and all that, what we can do is, since this is already an exponent, we can move it out front. So we have 3 times log base 2 of 4. So now what is the answer to this? Well, the log base 2 of 4 we know to be 2. So we end up with 3 times 2, which is 6. Now if you raise 4 to the third power, what you end up getting is log base 2. 4 times 4 is 16, times 4 is 64. And when you evaluate the log base 2 of 64, you're going to find that it's 6. So all we're doing is we're actually shorting ourselves a little bit in work because of properties that we know. If the log expression is looking for a power, and we already have a power out here, just move it outside. That's less work we're going to have to do. We've already got that power. We already have this power right here that we know. Now we can just evaluate what's left and multiply and get the answer that we're looking for. All right, so learning target number 2, logarithmic properties reveal that different transformations can have the same effect. It doesn't matter what it looks like, you can have the exact same equation, the exact same ending value. Now, logarithms of different bases can be related to one another, but they're very particular about the way that they can be related to one another. All right, so number 1, we're going to condense each logarithmic expression. Now, we only saw it as either plus or minus, but you can do it all in one. So with this one right here, what you can do is you could go ahead and do this part. You can do it in parts, and it makes a little more sense, but once you get the hang of it, you can do it all as one. So if we just combined these two right here, we would end up with a log base 3 of 4 times W. Let me write that a little better there. 4W. And then we still have this minus log base 3 of 7 that we haven't touched. So now this just becomes that second rule where we're doing subtraction, which means we're going to do division of what we're taking the log of. Remember, we checked up here, are the bases all the same? They were. And now we can combine them. So the log base 3 of 4W divided by 7. So that is condensed completely. All right, now over here, we're trying to get this as condensed as possible. In other words, a 1 log expression, nothing out front if we can help it, and go from there. So this part right here, we can do the opposite of that power thing that we were doing. 2 natural log of 5 is going to be the exact same thing as the natural log of 5 squared. Now, guys, please understand, this is not an algebraic thing. You cannot do this algebraically. This only applies because it's a log, because we're talking about powers, and that's what the end result of finding a log is to find the exponent. So we can move that up, and then minus natural log of 4. Now we can combine these two, and since we're subtracting, it's going to be division, and it's going to be 5 squared over 4, and you could rewrite that if you wanted to. You don't necessarily have to 25/4. I would leave it just like this. Now, if you need to, as we went through these, back up the video, look at it again, go back to the previous slide, look at those properties, and see how I'm using those properties. Here, I used the addition property on that one, and then once I got that combined into this, I used the subtraction property of logs on this one, and that put this all together. Here, I put the power property of logs on this, and then again the subtraction property on that. All right, so for number 2, we're completing the table of values for y equals 2 to the x and y equals 8 to the x, and then we're going to figure out an equation relating the two log versions of those. So 2 to the x, we're going 2 to the 0, that's going to give us 1. 2 to the 1 is going to give us 2. 2 squared is going to give us 4. 2 to the third is going to give us 8. 2 to the fourth gives us 16. 2 to the fifth is going to give us 32. And 2 to the sixth is going to give us 64. Now, 8 to the x, 8 to the 0 is going to give us 1. 8 to the first is going to give us 8. 8 squared is going to give us 64. 8 to the third is going to give us, let's see here, 32, 512. All right, calculator time. $4,096. $32,768. And $262,144. Now, what do you notice about these? So we've got log base 2 of x. And we've got log base 8. Oh, we wanted w. Let's do w. Could have just as easily been x. So now we're going backwards. All right, so here what we want to do, remember, with the log base 2 and the log base 8, we're now taking these values and we're going backwards. We're going back to find the x. So what we want to do is we want to compare the values. Remember, the w's here are equal. So what we're saying is, what happens if we plug in 8 to both of those? How is it different? And how do we make this thing equal? So if we do the log base 2 of 8 and the log base 8 of 8, what do we know the difference is? Well, the log base 2 of 8 is going to be 3. And the log base 8 of 8 is going to be 1. So what's the relationship here? Well, this one was multiplied by 3. All right, that's for that one. We would have to multiply it by 3. Let me change this color just so we know where it's added in. For these two to actually be equal. Now, let's check another set where we know that we have the same number that we're taking the log of and see if it works. So let's go over and do the 64. So if we do log base 2 of 64 and log base 8 of 64, over here we're going to get 6. Over here we're going to get 2. So what do we need to do to make those equal? We need to multiply that one by 3. So what is our equation that's relating these two? Well, that would mean that log base 2 of w, any value w we put in, would have to be 3 times the log base 8 of that same number. Now, here's the thing that's neat about this, though. What do you notice about 2 and 8? 2 to the third power gives you 8. And that is a property that you can know and you can use. 2 to what power gives me 8? 3. We'll just throw that 3 out in front of the log expression of the larger of the two. And now you've got an equivalent log expression. Now, in the same way, what you could do is you could work this backwards. This is an equation. It is an equation. So now, let's say you needed a log base 8 and find out how it relates to log base 2. Just divide both sides by 3. So 1/3 log base 2 of W is equal to log base 8 of W. So once you get the expression, it's equal, you can do the same thing you do with algebra with all of them. Just don't get inside the log expression. Inside the log expression is not algebraic. Remember, that's a function all to itself. But outside the log function, you can do everything algebraic that you normally can do. All right, number 3. The parent function of y equals log base x was stretched horizontally by a factor of 100 to create the graph of f. Which of the following transformations on the parent function would produce the same graph as f? All right, so if we stretched it horizontally by a factor of 100, horizontally, remember, is inside. Stretching and shrinking are opposite in there, so multiplying by 100 actually shrinks it, while dividing by 100 stretches it. So what we end up with here, the equation that we would make for this to be true would be y equals common log of x over 100. Remember, this common log is a log base 10 that's understood there. So now what we want to do is we want to find an equivalent expression that equals this that causes the exact same graph to happen. Well, all we're going to do is we're going to use those properties and rearrange this. Well, if we have a log, a common log, of x over 100, we can split that up, remember, into a subtraction. Remember, we can expand or contract. In this case, we're going to expand it. So log base 10 of x over 100 is going to be the same thing as log base 10 of x minus log base 10 of 100. Now, we can solve one of these logs because it's easy. Log base 2 minus, remember this is a base 10, so 10 to what power gives us 100? Well, that would be 2. So the exact same graph is going to be created by simply taking our log, sorry, I put a base down there. There's not a base there. Common log of x and just shifting the thing down 2 units. So C. So rearranging these gets us easier ways of graphing the exact same graph. Just using those properties to expand or contract to get it in a different form, we can find things out about the logs and their graphs and what's going on. All right, number 4. Chandler was asked to rewrite the log base 2 of 32a cubed, then simplify. Her work is shown below. In which step did Chandler make her first mistake? All right, so up here, we go from log base 2 of 32a cubed, and she splits, or he, split up the 32 times the a cubed. That's good. Log base 2 of 32 is 5. That's correct. Didn't do anything to the second log in the second step. So correct there. And then in the third step, we've got 5 plus 3 log base 2 of a. What they did there was take the power, move it out front. That's valid. We can do that. And that is correct. So 5 plus 3 log base 2 of a. And then step 4, we get 8 log base 2 of a. Well, that's where we made a mistake. The mistake is right there. You cannot combine these because this is a value. That's multiplication. Think about your order of operations. You would have to multiply this to get the value first before you could add those. So that's another instance where you got to remember your order of operations. This is 3 times log base 2 of a. We would have to evaluate this number, and then we could add the 5 to that. They added the 5 plus 3, violating the order of operations. Or you could also think about it as like terms. But I like my thoughts better. All right, hope that helped some.